Next up, we have Rob Habermeyer, who is going to give a Parachains update, where we are and what's coming. Rob?
Hey, thanks, Bill. And I just got the end of Gav's talk. That was a good one as well. Yep, so I'm going to be going into Parachains, basically how we got where we are, what's going to be coming up next. For a little bit of context, I'm one of the co-founders of Polkadot. I've been working on Polkadot with Gav since 2016. And I'm also the lead developer and team lead of the Parachains code base and implementation. So this is coming right from the horse's mouth. Well, first, let's dive into the the timeline, how we got here. We spent a lot of time sort of early on in the development cycle of Polkadot, just building substrate, building out those Babe and Grandpa consensus algorithms, building libp2p. So the development of Parachains actually was required a lot of those foundational components to be built ahead of time. So the first draft of the implementer's guide was in May. What the implementer's guide is, I actually have spoken about this a couple of times. It's basically a giant implementation document. What it is, it describes our motivations, how we think about writing a large piece of code like this, because when you dive into a large software development project, you really have to think about how are all of the pieces going to fit together. It's not something that can just emerge naturally of like, oh yeah, I feel like writing this today, I feel like writing that today. No, you have to, think about how that's all going to fall into place. So, if you're going to go somewhere like where we're going, launching Parachains, the implementer's guide, something like it, is incredibly crucial to make sure that that code is solid. This is a foundational infrastructure component. So that first draft, the implementer's guide, was sort of May 2020, once it was in a state where we could really start building on it in earnest. And what it essentially did was divide the Parachains code into 4 major parts. So those are backing and availability, which sort of go together, sort of validators finding blocks from collators and saying, hey, I think these are good, including those on chain, and then making sure that the data necessary to check them is there. The approval checking is the next thing. This is where really most of the security comes from. It's a way for, once parachain blocks are on chain, that validators randomly self-select in a secure way to see if they should recover that data and then check the block themselves. And then finally, disputes is this escalation aspect. So disputes are, if a validator detects that something is bad, then this needs to be escalated. It needs to reach all the other validators so that they can also participate and check it. Essentially, there's a very low, extremely low chance, right? We're talking about like 20 decimal points or something, that an approval checking phase goes through without someone finding out that the block is bad, and that would be immediately escalated. So these things all kind of fit together to give us the security and the scalability of Parachains. If you try to attack it, you're taking a 1 in 10 quadrillion chance that you're not going to lose millions of dollars. And that happens every single time you try to attack the system. So that's the code. Over the past couple of months, we've been employing SR Labs to do audits of the code, right? Checking the protocol, checking the implementation, trying to find bugs. And they've done an independent review. They've gone through various different components of the Parachains code base. Now, we use them for a bunch of other parts of the code as well, but specifically for Parachains, the audits were completed this fall. They raised a few issues, not many, and the fixes for those, as Gav mentioned in his previous talk, are around 50% done. And we have solutions in progress for the rest of those. So that gives us, this property of what we call technical readiness, which is after audits and significant deployments on Rococo and Kusama, Parachains are ready for an initial production release. Now, the caveat is we're going to fix those outstanding audit issues, and that's on schedule to be done before December. So the real-world deployments are also an incredibly important part of this. We have a Rococo test network, which I'll speak a bunch more about later, and that's the it's a multi region testnet that Parity runs all the nodes of. It has no economic value. It's literally just for trying out the technology. And we've seen, how this behaves with hundreds of nodes, for instance. We've also seen a real world deployment on Kusama. This is a totally different environment because you never know what's going to happen until it hits the real world. We can try to distribute it as much as possible on Rococo, but until it hits the real world, you don't know what's going to happen. And Kusama is an environment where you have 900 globally distributed validators. We have no idea who all of these people are. They're just running software on computers that they own or rent. And we've seen that on Kusama, it functions more or less correctly. So what does readiness mean versus maturity? What readiness means is that it works, but it isn't yet in its final form. The code is feature complete, right? It does everything that it's supposed to do. We've tested it, to a very high standard, various different edge cases. We've seen, that has the correct properties. We do that for various different modules and also in the ways that we stitch together those modules. It's been audited. There have been independent reviews by security professionals who have a high regard within the space, and it's been deployed, right? We've demonstrated to function even in adversarial conditions. We come up with the different ways that someone might attack the system, and then we actually implement those attacks, and then we see if the system keeps working. And actually, if you go and look at the Rococo testnet right now, there are adversarial nodes trying to destroy the network as we speak. They have not been successful. But when something is ready, it might still have bugs. There might still be outstanding optimizations. You can never know for sure. And that's where maturity kind of comes into place. Once something has really evolved to the point where it's been a foundational, heavily loaded, highly reliable piece of infrastructure, over the course of several years, that's when something is mature. So there are a lot of optimizations that can be done, something that's battle tested. For example, I take something like the Shanghai attacks on Ethereum, right? That was really battle testing Ethereum back in late 2016, where people were really going at it and trying to destroy the network. And when something is shown to withstand economic attacks in the real world, that's a huge step towards maturity. And the code is stable. It's maintained more so than it is developed. And that means that the innovation at that point is not happening as much on this level because its infrastructure and growth is occurring more at the fringes. So what is our road to maturity? What are some of the steps along that road? And I'm going to cover a few of the major ones, but not all of them. There's a lot of steps there. But a few of the I think really exciting things on the horizon are contextual execution, parathreads, and just general networking optimization. So I'm going to go into each of these three things, sort of break down what they mean. So if you've watched Parachains functioning on Kusama or on the Rococo network, you'd see that blocks are being included once every 12 seconds. Now, this is not a protocol limitation, but it's rather an implementation limitation, right? So contextual execution is the road to 6-second block times. Additionally, within those 12-second blocks that we have currently on Rococo and Kusama, there's only a short amount of time where block execution is actually occurring. The idea with contextual execution is to ramp that up significantly. It's basically about preparing blocks well in advance and sort of building the parachains further off-chain, and then slowly, bringing those onto the main relay chain instead of building the parachain block right before it gets included onto the relay chain. So that means that you're sort of preparing well in advance. And this is an optimization we have mapped out. We have a design for it, and it's one of the priorities for the next year. Another one of the interesting things that's coming up is parathreads. So that's a dynamic scheduler of parachain slots on a block by block basis. Well, what does that mean? Well, currently a parachain is something that has, it has dedicated execution time. It's buying via an auction 6 months or 12 months or 24 months of, dedicated, I get to make a block all the time whenever I want to. usage of the system. And what a para-thread is something for more of like a pay-as-you-go model, and it's very similar to a parachain. The code is really not particularly different. It actually only affects the what we'd call the backing and collation phases. So there's other phases that I mentioned earlier of availability, approval checking, and disputes. Totally the same for a para-thread. And in fact, it's the same thing for contextual execution. So the availability, approval checking, and disputes code is not needed to change for any of this future feature set that we're trying to do. The networking optimizations are just a big, right? This is peer-to-peer networking. As Gav mentioned in the previous talk, peer-to-peer networking is a challenge. It's very difficult, right? Because in a client-server model, you have to, you get to just ping some server and it comes back very quickly. When you're doing peer-to-peer networking, the challenge of distributing data as efficiently as possible, that means quickly and also with low redundancy, but high guarantees of delivery, it's very difficult to do. So there are a lot of, I'd say, fairly low-hanging fruit with respect to networking optimizations that are going to just help out the performance of the implementation substantially. So I think these are some of the really interesting things to watch out for on the horizon of Parachains. And coming up, I want to talk a bit about sort of this Rococo testnet. What does this mean for the community, and how can you guys get involved? Reframing Rococo. The Rococo testnet, I'll go into a bit. It's been a testnet, as I mentioned before, that Parity is running all of the nodes for, and it's been primarily focused on internal testing, basically bleeding edge code that we're running. We're modifying very quickly, deploying adversarial nodes, things like that. But it does mean that, as we've found bugs in the development process, we've occasionally broken the chain. That makes it a very difficult environment for teams to deploy their own parachains on. And Sub0 developers who are building parachains need to have a place to deploy and test cross-chain solutions. And I think, with XCM in the state that it is now, it's becoming more stable. It's something that people can really use. Those cross-chain innovation beds are going to be really important. So for that, we're introducing, what we're calling Rococo revamped. And the idea there is that, Parity will maintain backwards compatibility on the Rococo test network, ensuring that it doesn't restart or only rarely at pre-announced times, right? So when you register your parachain, you're not going to need to update your nodes or your runtimes, any more than you would have to for, say, something like Kusama or for something like Weston. That means that you can plan to use Rococo for a longer extended period of time and really use it as a place to cooperate with other teams. Another factor is automated parachain slots. So we've built a sort of scheduler of allocating time on Rococo to teams that register to use it. So they get, say, a week at a time, and these, week-long slots would be allocated to teams just automatically and fairly based on, availability. But we'd especially prioritize on Rococo teams that have deployed chains on live networks, because I think those are interesting. And we prioritize ones that are part of the Substrate Builders program, right? The ones that we're really helping with the technology and who have joined sort of our acceleration efforts there. And of course, this is a focus on community. We'd like to encourage cross-chain communication and experimentation on the Rococo network, right? Especially maybe at that higher level, not just of deploying parachains, but deploying things on top of parachains. I could see user interface or decentralized app developers that are leveraging multiple parachains, really enjoying this testnet as well, that it's not just for the super hardcore, low-level builders. I'll give a timeline on what that's going to look like. So today, I'm announcing our intention to revamp Rococo. We're going to follow that up with a longer form blog post that's coming soon. The technicals are being put in place. That means a new chain spec, reaching some of the parameters, things like, how long are the sessions, how often do the validators change, and things like that. We'd automate all of that, and then moving towards a launch of the final restart of Rococo that we would no longer use for internal testing. We're aiming for that at the end of November. And with that, I conclude my presentation. Thank you very much.
All right, thank you, Rob. That was really interesting. I'm really excited to see how Rococo evolves now. We had a few questions from the audience. First, has there been talk, or would you consider a battle testing event to community attacks on a test chain or even Kusama? Or is this something, these adversarial mechanisms you want to arise naturally or only with parity tests?
Well, I think the difficulty, right, is that somebody would have to be willing to risk quite a lot of real value-bearing tokens to carry out these attacks. We haven't observed it, or at the very least, if they have attempted, they have been unsuccessful. But the system is designed; it's a proof-of-stake system. It involves slashing, so it'd be very expensive. And I think at this stage, there are probably a few people who have both the technical skill and the financial backing to be willing to take on such a risk.
And I was wondering if you could talk a little bit more about some of the real world differences you've seen between Kusama and Rococo and West End and these test nets. You had mentioned you see different things, right, when you're in the real world with so many validators across the world. Can you give us some ideas of what these differences are and what you've seen?
Yeah, I think absolutely. There are a few. The two key differences that I can think of are networking, basically. These nodes are often not deployed on uniform hardware. They're often highly differentiated from each other. The latencies at which they establish messages and connections and can send those across, and also how quickly they can process those messages. It's highly differentiated to I think a degree that we haven't reached on Rococo. And on the other side is just node versioning, right? Like Rococo might have a few different versions of nodes, but I think on the main network, especially with substrates forkless upgrades, you don't have that uniformity of versioning. A lot of validators don't upgrade their nodes that often, so they're running with slightly different versions of the consensus code, and I think this can also it would be a factor for emergent effects that you wouldn't see in a more clean room testing environment.
Are you trying to emulate some of these things, like different versions and artificial latency or something in the test nets, or are you just?
Yeah, what we've done is Rococo is deployed over several different regions, so globally. So those will have different latencies on the as well as having different nodes on some different versions, especially custom versions, especially ones that carry out attacks. Most of the stuff with respect to checking custom delays and things has been done not on Rococo but in other environments, right? That we have some Docker image that we've used internally for gating network messages for specified amount of times, or acting as though a node is on a very slow internet connection.
So on that note about these adversarial nodes on Rococo, can you say what are some of the the attacks or adversarial mechanisms they're doing? Are they spamming the network? Are they giving bad messages, or a variety of things?
So primarily, it's about the protocol itself. So we've got nodes that are reporting valid parachain blocks as invalid, and we want to see if this affects that gets detected. They're wasting everybody's time. They're escalating something to dispute, and that they're getting reported and detected. The dispute is getting resolved. And on the other side of that, and this is the more important attack, we're checking that an attacker or a group of attackers who collude to include a bad parachain block are detected, right? They're detected by those approval checkers who then escalate it to disputes. And then those attackers get slashed and they're getting punished. But furthermore, that the relay chain then sort of reorganizes to avoid the bad parachain block. That actually affects the fork choice rule of the relay chain. So you're sort of building a chain in one direction and detect that, oh, there's something bad in this chain, and then you just sort of go backwards and everybody starts building a new chain. And, this has been running on this class of attacks has been running on Rococo for a couple of weeks now.
And one last question. So on this note of approval checking, can you explain how this is, like the current system is different from the original model with fishermen? Since I know those the idea we've sort of deprecated. Can you sort of explain quickly the difference between how those worked and what we're doing now?
Yeah, so the original design was looking a lot closer into fishermen, and the background there was that you have just user operated nodes, say even collators, that are watching for bad stuff to be included, and if it is included, then they'd detect it, they'd submit a fraud proof, and basically earn a reward by doing that. So that had a number of issues. Basically, one, you need to delay finality for a fraud proof period. It means that you're going to have slower throughput, slower settlement, right? So that's kind of a design fallback of using fishermen. And the other thing is, sort of the way the proof of stake works is that, like, because they're slashing, nobody attacks the network, so no slashing happens, right? And if you have something like fishermen, right, as a defense mechanism, attack events are going to be, very rare because it does work, right? It's not as fast as we'd like. But then you run into the situation where attacks are incredibly rare. When an attack occurs, the fisherman nodes are all competing to get the payout, and only one of them will actually get that payout. There are a couple of maybe ways that you can improve on that, but not really substantially. We even thought of like introducing forced malicious behavior to do that. And essentially what that means, you could run into a situation where nobody is a fisherman, and that's not something you want to rely on for security. So we came up with a different system, which is based more on like random self-selection, just like incredibly low probabilities of an attacker being able to get away without somebody honest checking their block. And this means that we can have faster finality. We're not relying on fishermen to actually exist. The validators actually get rewarded for participating in this system. And furthermore, it can be augmented in the future. We actually plan to do this, is to augment it with a user-initiated dispute system.
All right. Well, we actually have many more questions, but unfortunately we're out of time. So thank you very much, Rob.